Welcome to this explainer. Today, we're diving into the invisible, abstract forces that literally hold our physical universe together. We look at solid objects every single day, right? Our desks, our phones, even our own hands, but we rarely stop to think about the microscopic architecture, keeping it all intact. Well, today, we're making the invisible visible. But before we get lost in the weeds of complex theories and mathematical models, we really need to ask the fundamental question that has been driving chemistry for over a century. How and why do elements combine to form the world around us? It isn't magic, It's a very specific set of rules. Here's our roadmap for today. We'll start with a quest for chemical stability, dive into Valence Bond Theory and hybridization, unpack Molecular Orbital Theory, compare all these models, and finally, wrap up with the unified bonding toolkit. All right, part 1, the quest for chemical stability. Let's start with the ultimate macroscopic goal of literally every single atom out there. The universe is, well, kind of lazy. It really just craves stability. Atoms are constantly seeking a lower energy state, and they achieve this ultimate relaxation by bonding. More specifically, they want to reach that perfectly balanced, noble gas configuration. So today, we're going to focus sharply on covalent bonding, which is the sharing of electrons, and the absolutely amazing theories scientists came up with to explain exactly how this sharing works. Moving into part 2, Valence Bond Theory explained. So our first crack at understanding these covalent bonds is actually super intuitive. Valence bond theory, or VBT for short, is kind of like puzzle pieces snapping together. This theory states that a bond is quite simply the physical overlapping of half-filled atomic orbitals. If I have an atom with a lonely unpaired electron and you have an atom with an unpaired electron, we literally smash those orbital spaces together to share them. This brilliantly illustrates the step-by-step mechanics of how a bond forms. Two atoms approach, their atomic orbitals physically overlap, the previously lonely electrons pair up happily, and boom, you've got a localized covalent bond. The golden rule here is incredibly simple. The greater the physical overlap between the atoms, the stronger the bond is going to be. VBT also perfectly explains directional bond strength. If atoms crash together head-on, you get what we call a sigma bond, a really strong, highly overlapping connection. But if they overlap parallel to each other, sort of side by side, you get a pi bond. Pi bonds have weaker overlap, and they're basically the secondary connections you'll find stacked up in double and triple bonds. But hang on, there's a massive blind spot here. VBT works great for simple localized bonds, like two hydrogen atoms coming together. But it leaves us with a huge problem. If we just smash atomic orbitals together, it completely fails to explain the complex, real-world 3D shapes of molecules we actually see in the lab. And even weirder, it absolutely cannot explain why liquid oxygen is magnetic. Which brings us to part 3, hybridization, shaping the molecule. To fix this 3D shape problem and build a better model, chemistry introduced a brilliant mathematical patch. Because VBT alone just wasn't cutting it for molecular geometry, scientists introduced hybridization. Imagine taking a spherical s orbital and 3 dumbbell-shaped p orbitals on the exact same atom, throwing them in a blender, and pouring out completely new, equivalent hybrid orbitals that point in entirely new directions. This mathematical trick flawlessly explains the stuff that VBT couldn't. Take methane, for example. Why does it look the way it does? Well, hybridization proves that carbon mixes its orbitals into 4 perfectly equivalent sp3 hybrid orbitals. They push away from each other equally, creating this precise tetrahedral bond angle of exactly 109.5 degrees. It literally gives us the architectural blueprints for almost all standard molecules. If it's sp hybridized, it's a straight line. If it's sp2, it's a flat triangle. If it's sp3, we get that 109.5 degree tetrahedron. And what's really fascinating is that unshared electrons, lone pairs, they take up physical space too. They slightly bend those perfect angles, which, by the way, is exactly why a water molecule has its distinct bent shape. Okay, so the 3D geometry problem? Solved. That's fantastic, but this mathematically patched, localized model still cannot explain our other glaring problem, the observable paramagnetism of oxygen. Seriously, if you pour liquid oxygen through a powerful magnet, it literally sticks to the poles. Neither VBT nor hybridization can tell us why that happens. So what are we still missing? Let's crack that in part 4, Molecular Orbital Theory Explained. To solve this magnetism mystery, we have to zoom way, way out and look at the whole picture. Enter Molecular Orbital Theory, or MOT. This completely changes the game. It says, hey, let's stop looking at bonds as just local traffic between two neighboring atoms. Instead, when atoms come together, their atomic orbitals merge to form entirely new global molecular orbitals that map across the entire molecule. The electrons are no longer tied down to one spot, they are delocalized. So instead of just localized overlapping, electrons now fill these new global orbitals based on their energy levels. And here is the wild part. They can either fill stabilizing bonding orbitals that hold the whole molecule together, or they can fill anti-bonding orbitals. These are higher energy zones that actively try to rip the molecule apart. It's literally a microscopic tug of war. By taking the number of stabilizing bonding electrons, subtracting the destabilizing anti-bonding electrons, and dividing by 2, we get a precise calculation called the bond order. And if that calculation comes out to a big, fat 0, it instantly and mathematically proves the molecule is completely unstable and just cannot exist. But here is the absolute best part. By tracking this global electron behavior, MOT mathematically proves that an oxygen molecule actually has unpaired electrons hanging out in its high-energy anti-bonding orbitals. And what do unpaired electrons do? They create a magnetic field. MOT finally solves the mystery of oxygen's paramagnetism that the older theories couldn't even touch. Moving on to part 5, comparing the bonding models. So, with 3 different explanations for how atoms connect, you might be wondering, which of these models is the correct one? Well, when we put VBT and MOT head-to-head, you'll see they are entirely different lenses for viewing the exact same phenomenon. VBT looks at localized overlap, it's simple, it's intuitive, but it misses the big picture stuff like magnetism. MOT looks at the combination of orbitals into a delocalized global map. It's highly accurate and explains magnetism perfectly, but man, is it mathematically intense. So, the crucial takeaway here is that ultimately it's a comparison of utility. Valence Bond Theory provides a fantastic qualitative snapshot. It gives you a really fast, easy way to visualize a bond. Molecular Orbital Theory, on the other hand, delivers rigorous, highly accurate quantitative data for when you need to know the exact magnetic and energetic realities of the molecule. And finally, Part 6, the Unified Bonding Toolkit. This brings us to the final, brilliant twist in our molecular detective story. Actually, you don't throw away the older, simpler models just because a more complex one exists. Instead, you integrate them all as a complementary toolkit. You use VBT to quickly see where the bonds form. You use hybridization to understand why the 3D shape looks the way it does. And you pull out MOT to calculate exactly how the electrons are behaving on a global magnetic scale. By combining all 3, you gain a master key to understanding how the universe holds itself together. So the next time you tap your desk, ask yourself, which of these invisible forces are you really feeling?